Okay, next up. This is a little bit longer. Yeah, this is a little bit longer, but actually we're going to kind of breeze through the last little part. So let's talk about the idea of solubility. So there are certain factors that affect solubility, how much something can dissolve, because we've looked at different types of solutions. Now let's look at the factors that affect solubility. So chemists use the idea of like dissolves like, much like when we were looking at the intermolecular forces. When they have similar intermolecular forces, they tend to dissolve, and so on and so forth. So ultimately, it comes down to these two ideas. Polar dissolves polar, and nonpolar dissolves nonpolar. That's it. That's the idea. And typically when you are in the lab and you're actually doing this, we are going to refer to polar compounds as things that dissolve in water. So we're going to say aqueous. So polar dissolves like. Salts, right? So aqueous, so water, loves things like acids, loves things like salts. Again, whenever I say salt, what I really mean is an ionic compound, metal and non-metal, right? So acids, some kind of bases, again, that's ionic as well, but that's what water loves. Yeah, bases. Okay, which are an offshoot of salts, really. And then nonpolar dissolves nonpolar. Whenever we say nonpolar as chemists, typically what we're talking about is organics. So whenever we say the term organic, we're talking about some combination of carbon, hydrogen, and other stuff. So R is, I don't know, nitrogen, some combination of nitrogen or oxygen, or some kind of halogen, so some combination of those things. So whenever I say organic, we're talking about large organic molecules, a bunch of carbons, a bunch of hydrogen. So if you see carbon first, that's generally going to be nonpolar. Okay, so like dissolves like. And so let's prove this by looking at the solubility table. So what we have here are a bunch of different alcohols. I've got methanol all the way down to hexanol. So we're just increasing. Methanol is one carbon. Ethanol, eth means two, right? So meth means one, eth means two. 3 carbons for prop, 4 carbons for bute, 5 carbons for pent, and 6 carbons for hex. So they're getting increasingly longer. So what we're doing is, can imagine how polar this is just by the fact that we have this OH group. So I'm going to put some R group there. That's just, so we have this side, which is polar, and we have this R group, which is nonpolar. So the longer that nonpolar size gets, or the bigger it gets, the more carbons in a row, the more nonpolar the molecule gets, because you're dwarfing the size of that hydroxide. So as we increase the size of that R group, or we increase the length of that carbon chain, we're getting a decrease in polarity. So polarity is dropping as we go down. Does that make sense? Because the hydroxide is going to remain the same strength, but that dispersion forces are getting stronger and stronger and stronger. Well, what is the solubility in water? Well, we know that solubility of water is polar, and C6H14, that's a C, just carbon and hydrogen, so we know that's going to be nonpolar. Again, what's another word for this? This is organic. This is aqueous. It is the aqueous, but again, get used to that. Whenever I refer to something that's organic, I'm talking about nonpolar. Aqueous is typically going to be polar. So what do we see? Well, up here, we see a very large solubility. And as we go down, notice that the solubility decreases. So solubility decreases as what's happening. So again, like dissolves like. If this is very polar and this is very nonpolar, what we're typically seeing is that makes sense, because it should dissolve in water, and then at some point it's going to dissolve less and less in water because it's going down. And the opposite is true for the organic. We'll notice that the methanol actually is barely soluble in hexane, or the C6H14. But everything else is soluble, because again, we're getting this decrease in polarity. So ultimately, what do we see is as polarity decreases, we see an increase in solubility in organics, which is nonpolar. I should separate that. In organic solvent, and a decrease in solubility. Solubility, there we go, in aqueous solvent. Okay, makes sense? Good enough. So again, that's the idea. We see that change. And again, if we point out what forces help acetone dissolve in water, again, we have to recognize that water is polar. Right, there's a partial negative up here, there's a partial positive down here. It is in fact polar. Sorry, that's the other way. Ooh, I did that backwards. Okay, it is the other way. Here we go. This is hydrogen bonding and dipole-dipole, and acetone is going to have the same exact thing. Right, acetone is going to have that polarity. So they're both polar. If both of these are polar, we expect them to mix. Okay, and in fact they are. So there's two new terms that I want to introduce. The idea of miscible. This is miscible. They mix. So the liquids layers mix, all because again we have these polar molecules, water and acetone, and they're going to line up so they can interact with one another. Okay. And polar dissolves polar. But when we look at something like this, which is immiscible, immiscible just simply means that they were not going to mix. So we have two different layers. Down here, I have the organic layer, and up here, I have the aqueous layer. Right. So those two things, that's the water layer. And we have these polar compounds. And the dichloro, the CH down here. So I have water up here. And down here I have CH2Cl2. Turns out that these are actually not strong enough. They're polar, but only slightly so. So the cohesive forces are greater than the adhesive forces. So they prefer to interact with, they prefer to stay together. So this is immiscible. If you shook this up, you're going to see these things separate out. So this is like having oil and water. Oil and water are immiscible. They're not going to mix. You can use something like a surfactant or an emulsifier to actually make them mix. But if you mix them up, eventually they're going to spread apart. So that's the idea. Those two terms, miscible and immiscible, they mix or they don't mix. So with that said, we're going to do these in class, but vitamin A is nonpolar, and there it is right here. Why do we always get these things? And then, I'm sorry, vitamin C is polar, which is right here. And of course, it's polar. This one's nonpolar because it has this large organic along with just that small hydroxide. This has got some organic, but it has a lot of hydroxides, which allow it to interact with water. So the question is, why do we run into that situation where we're always told to drink orange juice in order to get enough vitamin C? Why do you not hear any advertisements for, hey, you've got to consume a bunch of stuff in order to get vitamin A? You see stuff for, you need to get a lot of vitamin C. And so we're going to talk about that in class. We've done this kind of idea before. Which of these do you expect, and then we're going to do this in class, arrange these substances in an order of increasing solubility in water? So which one is the most soluble, which one is the least, and tell me why. All right, so let's take a look at gases in solution. So gases in solution, gases are going to be important in solution. And I just remembered we're not going to actually go through this stuff in class because I said that I would just assign it. So I will come back to these. I would encourage you to pause it at the end and come back. Well, I'm going to come back to these at the end of the lecture. So gases in solution. It's pretty simple. The only forces that really hold gases together are the amount of London dispersion forces. So in terms of solubility in gases, the greater the molar mass equals an increase in size. Increase in size leads to greater polarizability. More polarizable equals increased in the induced, it increases the size of the induced dipole effect. Increasing that dipole effect and increase in dispersion forces, or LDF, I'll say, equals an increase in solubility. So ultimately, the larger it is, the more soluble it is. And that is in fact exactly what we see. If we compare nitrogen to krypton, we notice that krypton is significantly more soluble than nitrogen is in solution. So gases are this kind of weird thing. Gases, the solubility of liquids and solids does not really change with pressure, but that is absolutely not true of gases. So solubility of gases is directly proportional to pressure. Directly proportional to pressure. So if I increase the molar mass, I increase the solubility because we're improving the intermolecular forces. If I increase the pressure, I'm going to increase the solubility. So increasing pressure increases solubility. In fact, we have a relationship with Henry's law. So Henry's law it is going to the solubility of some gas is equal to, I'll identify these two shortly, is equal to Henry's gas law constant times the pressure of that same gas. So one more time, this is the solubility of gas G. K is the Henry law constant, Henry's constant. Henry's constant of gas G. That's a terrible G. G, there we go. And PG is the partial pressure of gas G. Okay, good. And so here is the solubility chart of partial pressures. Again, what we notice is as pressure increases, as we increase pressure, solubility goes up. What you do notice at zero pressure, it should go through zero, right? At zero pressure, there should be zero solubility of gases. But as pressure increases, so does solubility. It is always that true for gases. So this is the practice problem using Henry's law, determine Henry's law constant using this. So again, I'll come back to this at the end and complete all these. So temperature and solubility of gases. So we talked about molar mass and pressure affecting solubilities. Temperature does as well. We know that as we increase temperature, we see a decrease in the solubility of gases. That's the trend, okay? Gases are always going to remain constant. There is no like exclusions for this. Gases behave how they behave. And you're going to see that solids do not always behave that way, and liquids don't always behave that way. So as temperature increases, there's a decrease in solubility of a gas. Good. So these two questions, again, I'll come back to these. Why, and I was struggle saying this, why do mountain lakes lack the presence of fish? And another question is, nuclear power plants use water to cool the reactors before it is released into the local watershed. What problems are caused by adding warm water to surrounding wildlife, particularly to fish? So we'll talk about that when I come back. All right, solubility. So this is an important kind of graph to understand, to be able to read. So what do we notice here? So take a moment and kind of pause this and take a look through this graph. Okay, some things that you're going to notice is, first of all, some trends happen to be linear. Some trends happen to be exponential in nature. And in fact, some cerium and barium compounds typically do this, but some actually decrease with increasing temperature, right? Temperature is increasing and we actually see a decrease in the solubility of cerium sulfate, which is a really weird thing because you typically always think, oh, increase the temperature, we're increasing the solubility. And so that's not always true. So with that said, let me ask a couple of questions. So first of all, let's just focus on a really simple one. Let's just focus on potassium chloride. Okay, so we're going to take a look at potassium chloride. And I'm going to ask you two questions. First of all, at 100 degrees Celsius, how much KCl can be dissolved? Okay, and I want to point out one quick thing is notice the solubility table. The unit for solubility is grams of salt in 100 grams of water. It's a really weird unit, but that's typically what they use. It's not like a molarity or anything. It's grams of salt in 100 grams of water. So how much at 100 degrees Celsius, how much KCl can be dissolved in 100 grams of water? So just using the chart. So that means how we're going to do this is I'm going to look at, all right, so I have 100 degrees and I'm going to go up until I hit the line, and right here, that looks to be about, I don't know, 50, actually that was a bad line, about halfway up, right? So about halfway up, maybe a little bit more, so let's say 56. So that right there is 56. So I'm going to say 56 grams per 100 grams of H2O. So KCl. 56 grams KCl per 100 grams of water. Okay, so we've kind of moved up to see where we're at. Okay. At 30 degrees Celsius, how much KCl can be dissolved? And actually, before we answer that, let's just quickly go back to think about this idea. So notice that we're right on the line. So on this line, if we're actually on this line, that is a saturated solution. If we actually create that solution. Anything above that line is going to be either saturated or supersaturated. The only way you can tell the difference is by observing it. So if I say I dissolve 100 grams of KCl in water at 100 degrees Celsius, and I notice that there is solid on the bottom, okay, so saturated, we would have to observe the fact that, all right, we have this pile of solid on the bottom, there's KCl. If I have that pile of solid on the bottom of my beaker, that means that it is in fact a saturated solution. A supersaturated solution would just simply be, all right, well, actually everything is dissolved, and it shouldn't be. It should be crashing out of solution. So on the line is supersaturated. Above the line is either supersaturated or saturated, and we have to identify what's going on physically. And then below the line is always going to be considered unsaturated. Okay, so at 30 degrees Celsius, how much can actually be dissolved? And at 30 degrees, you're about here, which makes it about, what is that? I don't know, 34. So 34 grams of KCl per 100 grams H2O. Okay, makes sense? Great. So answer this question for me. A sample of potassium nitrate, 50 grams is dissolved in 100 grams of water at 100 degrees Celsius with precautions taken to avoid evaporation. It is cooled to 30 degrees. Explain the state of the solution and what you'd expect in the following situations. So we're just going to do this one right now. So let's highlight the solution that we're talking about. So we said potassium nitrate. There's my potassium nitrate line. So potassium nitrate, all right? And so it's at 100 grams and 100 degree at 100 degrees. So 100 grams at 100 degrees. Oh, sorry, 50 grams is dissolved in 100 grams of water. Yeah. 50 grams at 100 degrees Celsius. So 100 degrees Celsius, 100 grams of water. So right here is where we're going to mark it. Is dissolved with precautions to avoid precautions to avoid evaporation of any water. The solution is cooled to 30 degrees Celsius. So we're going to cool this thing to 30 degrees. So cooling it down to 30 degrees, there's my 30-degree mark. And here we go. So we have essentially just gone in this direction to reach here. So this is the final state. Okay. So I had 100 so I now have 100 grams at 30 degrees. That's, or sorry, 50 grams. I messed that up. Yeah, sorry. Let me back up just a little bit here. Sorry about that. So one more time, 100 degrees, 50 grams. So right here, it's not going to actually change our answer at all, but that's what it actually should be. There we go. There we go. And then we cool it down to 30 degrees, puts us right here. Okay, so this is our final spot. Yeah. All right, good. So if we observe no precipitation, so first of all, in its state, is it above, on, or below the line? It is above the line. So that means that it can either be saturated or supersaturated. If no precipitate is observed, it is going to be supersaturated. If we see a precipitate, okay, that means that it is in fact saturated. And now the question is, how much precipitate is expected? Well, we have 50 grams and we expect it to be there, which is about 45 grams. So let me just write this out. So the idea is we expect solution to hold only 45 grams, but it's trying to hold 50. So if we do see a precipitate, we would expect to see 5 grams of precipitate. Again, that is because if we look at it, it has 50 and it can only hold 45, meaning that delta right there is going to be what precipitates on a solution. Okay, that makes sense. Hopefully you know how to read that. Hopefully that makes it all work. Next up, mass percentage. I'm just going to quickly go through these. We've already done these. Again, mass of whatever, substance A, mass percent of substance A is equal to the mass of A over the total mass total of all things present times 100. Again, you need to know these. Parts per million, parts per trillion. Parts per million is X over 100 if you're going from percentage, or I should say percentage. You can set up a proportion. So if it's like 3 percent points, it's X over 1 million. But parts per million is in milligrams per liter. Parts per billion is in micrograms per liter. That's typical. And then mole fraction, we're going to use a decent amount. So mole fraction of A is moles of A, substance A, over moles total. Not times 100, the number should be between 0 and 1. Molarity is, again, moles of solute over liters of solution. And molality is equal to moles of solute over kilograms of solvent. And in order to go from molarity to molality, you need density. And then we have a bunch of practice problems, which we have done all of these, but they're worth going if you want to. And then we're going to move into colligative properties. So this is it, but I'm going to go back and do the problems that we had just quickly. Yeah, I'll do them in the proper order too. So let's start with the idea of vitamin A being nonpolar, like fats. So vitamin A is nonpolar. So typically what that means is we consume it and it stays in our fat. and it stays in our bodies. Vitamin C being polar, it prefers to interact with water, meaning if it interacts with water, we have to keep consuming vitamin C because it goes out with our excretion. Essentially, we just urinate it out because it's constantly interacting with water. So the vitamins that are fat soluble stay in our muscles, stay in our fat, stay in our body. Anything that's water soluble just keeps getting pushed out. So that's why you have to eat vitamins and minerals pretty regularly, especially things like sodium, potassium, magnesium, all of those things to make your body run. If you don't consume those regularly, because they're ions and they like to interact with water and they just get flushed out of your system. In fact, that's one of my big things is I need to keep drinking G2 because I need those salts continuously. So with that said, arrange these substances in order of increasing solubility in solution. We're going to treat this the same exact way that we did boiling point. So if we look at this, this is nonpolar. A is nonpolar. That means it has London dispersion forces. B is polar. So it has London dispersion forces and it has dipole-dipole. Does it have hydrogen bonding? Yes, it does. It has hydrogen bonding as well. C is polar. It is going to have London dispersion forces. It is going to have dipole-dipole. Does it have hydrogen bonding? Yes, it does, because it's got that OH. And then finally, C is considered polar. It has London dispersion forces. It is dipole-dipole. Does it have hydrogen bonding? No, it does not have hydrogen bonding because it doesn't have nitrogen, oxygen, or fluorine. So there we go. So in terms of solubility in water, the least soluble to the most soluble. Right away, we can say things that are unlike water. Water, again, we know that water is going to have, we know that water is polar, very polar. We know it has London dispersion forces. We know that it has dipole-dipole, and it absolutely has hydrogen bonding. So if it has all of those, we know that A is the least like it. So A is going to be the least soluble. D is going to be maybe a little more soluble in water, but because it doesn't have hydrogen bonding, it's going to do less well, I guess. And in terms of the two, B or C, I have one site for hydrogen bonding versus having two sites for hydrogen bonding. That means C followed by D being the most soluble. Again, this just comes down to like looking at those values or just looking at the forces holding them together. All right, good. Henry's law. So this one is pretty straightforward. This is a pretty simple problem. So the solubility of my CO2 is equal to Henry's law of CO2 in that case, times the pressure, I guess we'll say CO2, times the pressure, partial pressure of CO2. All right, so the concentration of CO2 in a soft drink, I did look these numbers up, is bottled with a partial pressure of CO2 at 4 atmospheres. So that means that we have 4.0 atmospheres for the partial pressure of CO2. I know that we're looking for K, lowercase k of CO2. Over the liquid at 25 degrees Celsius. Okay, so we have a temperature associated with it. I don't think we need that, as 1.2. So that's the solubility of 1.2 times 10 to the minus 1 molar. Henry's law constant. So K CO2 is equal to, and I'm just going to take 1.2 times 10 to the minus 1. I don't know why I'm doing that. I should just turn it into regular notation. So 0.12 molar per 4.0 atmospheres. Okay. And so what you end up with is 0.030 molarity per atmosphere. So what that means is for every single atmosphere you apply, you're getting 0.03 molar more into solution. That's it. That's Henry's law constant. That's that calculation. Good. Next up, these two questions. Why do mountain lakes lack the presence of fish? Increasing the altitude does what for the pressure? Increasing of altitude means there's less stuff weighing down because we're closer to the atmosphere, or basically closer to space. So it decreases the pressure, in particular pressure of O2. So if we decrease the pressure of O2, decreasing pressure has this same effect on solubility. So we decrease the solubility of O2. No oxygen equals no fish. So if we have a low concentration of oxygen in solution, means that we're not going to have any fish that are able to survive because they need dissolved oxygen in order to be able to survive. All the reason that heating up of oceans is a very dangerous thing because we're essentially going to kill our fish. Same thing here. Increase in temperature from like nuclear runoff, nuclear reactors releasing heat. Increasing in temperature for gases is going to decrease the solubility of O2. By decreasing the solubility of O2, we have a low oxygen environment. Low oxygen, again, no fish. So again, that's just goes back to those relationships. Pressure and solubility of gases are proportional, and temperature and solubility are inversely proportional. So we just need to know those. And I think that is it for this. Yes. Yeah, you can do those calculations. We already did those, so you can look them up. We're going to start colligative properties next.